In this video, we're going to example the pooled two-sample t-test. Let's make a note of that. This is going to be done with pooling. Now, if you're not told to use pooling, the way to determine that is to compare the ratio of the standard deviations. So the sample standard deviation for the first sample is 3. The second sample has a standard deviation of 5. And you take the big one, dividing it by the little one. If the ratio is less than 2, you're going to use pooling, unless you're told otherwise, of course. So what's our problem statement? Well, we have samples from two sources, and we want to determine if they come from the same populations. First sample is size 32, so this would be N1. The mean is 22, so we'll call this Y bar 1, with a sample standard deviation of 3, so this is S1. Second sample has size 30, that's going to be N2. 5, we already noted, that's S2, and Y bar 2 is 24. Okay, there we go. That's all we need to do this, except we need the hypothesis, of course. So let's sketch that out. So the null hypothesis always suggests in a test like this that the two means are essentially the same. Now I've noticed that the mean of 24 is a bigger number than the mean of 22, so I'm going to be a little bit creative here and go mu2 minus mu1 is equal to 0. And the reason I'm doing that is simply to avoid a negative sign. Now, if you're told to do otherwise, well, do what you're told. However, when you have a choice, I'd like to not be bothered by having to deal with negative signs. That's a personal preference. Now, what do we want to know? Do they come from the same populations? Well, that kind of implies that they're significantly different if that's the case, because usually the means would be different in two different populations, and probably the variances as well. So the question is asking here, does sample 2 have a significantly larger mean? So that means this is going to be greater than 0. How I would come to recognize that if I was having trouble parsing the problem is I would say, well, in the null case, mu2 would be equal to mu1. But now I'm interested in, is mu2 actually bigger than mu1? So I'll just change this to a greater than symbol. Then algebraically I'll move that across. So mu2 minus mu1 provides a positive number. So that's one way you can figure this out if you need to. The alpha level is 5%, level of significance I should say, so we'll set that up there. That's a one-tail test, so we'll just use the raw p-value from the one-tail probability row on the t-table. Now, since this is pooling, we do have a fairly lengthy computation. Formula is, we're going to go y2 minus y1, or pardon me, y bar 2 minus y bar 1. But we've got two square roots to deal with. First one is n2 minus 1. Whoops, bumped the button. There we go. And we're going to have standard deviation 2 squared. And then we'll have n sub 1 minus 1 and s1 squared all over n2 plus n1 minus 2. And by the way, this will be our degrees of freedom for this test. Here it's 1 over n2 and 1 over n1. Let's give ourselves a little bit of room to work. Move this up a little bit. Now, let's put some numbers in. So this is 24 minus 22. Now, sample size for the second sample, let's just come back up here a little bit. There we go. We have size 30, which means we have a 29 here. And then we're going to multiply that by the square, the standard deviation. And that is 5. First sample is size 32, so we put a 31 here. and its standard deviation was 3, so we'll square that. So we have 30 plus 32 minus 2, which means our degrees of freedom are 60. This will be 1 over 30 and 1 over 32 on this square root. Now, the numbers. What do we get? Well, this is 2. I don't need a calculator for that, I hope. At least not yet. I know I'm getting old, but I'm not that old that 24 minus 22 is actually 3. Don't write that down, by the way. Just kidding. So the first square root is 4.091. I'm only going to use 3 decimals. And then the second square root is 0.254. Now, we multiply that denominator. Our total standard error then is 1.03. Oh, well, that's actually 1.39 and then a 5. So let's just back that out. Undo. This is going to round to 104.0 at 3 decimal places. And of course the top is this. So what do we get? Now, let's just double check on that because I rounded that number. 2 divided by 1.04 gives me a test statistic of 1.923. Now, if you're asked for the distribution of the test statistic under the null hypothesis, we have a nice little summary right here. The test statistic is in the family of t. Its value is 1.923 and is on degrees of freedom 60. So that tells the reader, if they wanted to check your p-value, how they can verify it. Which I guess we should do next. So let's go to the t-table. We have 60 degrees of freedom. Well, we'll scroll all the way down here. So here is row 60. And our test statistic of 1.9 is right in there. Now what is that? What does that tell us? Well, we've got to go back to the top to see it. So this is between columns 2 and 3. So we're going to go up here, which means our p-value is right here. Our p-value is smaller than 5%, but bigger than 2.5%. And since the result there is smaller than our level of significance, our p-value is less than alpha. Our conclusion then is we do have evidence to reject the null hypothesis at the 5% level of significance. We're going to do a confidence interval as well, but we'll do that in a second video. These get to be a little bit long and tedious. So we'll call this one done, and on the next video we'll do the same numbers with a confidence interval. And that ends this video.